Up till now, we've been looking at limits at specific x values and essentially looking at whether or not the graph of our function came to the same y value on both sides. Today, you're going to look at limits way to the right or way to the left on your graph. In other words, limits at either infinity or negative infinity. Loosely speaking, a limit at infinity, if it exists, is the single y value a function approaches by making x arbitrarily large. So in other words, the larger I make x, what number do I appear to be getting closer and closer to as I make x big? Let's jump into Microsoft Excel and take a look at what things can happen when we try to do these kind of limits. Okay, feel free to follow along because you'll be doing these same kind of calculations in class on a couple problems. I'm going to put in column A my x values, and we're going to look at three different limits at infinity, these three functions here. So I'll go ahead and label the columns for each function. So the first one will be 2x minus 10 over 5. The second one will be 5 over x plus 3. And the last one will be 3x squared minus x minus 2 divided by 5x squared plus 4x plus 1. Now, when we say we're taking a limit at infinity, we're saying we're going to make x as large as we like. So what I'm going to do is start x off at 100 and just make x bigger. So we'll go to 500 and then maybe 15,000 and then maybe 250,000, and we'll end up with 4 million, I guess. And we could add more values if we like, but hopefully this is enough to get the general idea. So we're going to ask Excel to calculate the value of this function at these x values. So remember that starts off with an equal sign. We want to do 2 times the value in this cell, A2, minus 10, close parentheses, divided by 5. And then I will double click on the small blue square and it should fill down the values for me. Okay, so based on the evidence I see here, it looks like as I make x larger and larger, it looks like the y values also get larger. So I'm tempted to say, based on this evidence, that this first limit is going to be infinity or does not exist. Obviously, this is not a proof, but it's a suggestion using numerical data. Let's take a look at the second example. This time we're going to say equals 5 divided by, parentheses, cell A2 plus 3, and press enter and fill down. Now I'm going to drag off my cell width a little bit bigger and take it off scientific notation and add some decimal places, because look what's happening here. As I make x larger, looks like the y values are getting smaller and smaller. In other words, they're getting closer and closer to 0. We keep adding zeros after the decimal place. So I'm tempted to say that the second limit is going to be 0 based on this evidence. Let's look at the last one. This one's got a lot more to type, so parentheses, 3 times cell A2 squared minus cell A2 minus 2, close parentheses, divided by, parentheses, 5 times cell A2 squared plus 4 times cell A2 plus 1. Close the parentheses, and let's fill this guy on down. Now, this one's kind of interesting because these numbers are getting closer and closer to 0.599999, which tends me to say that they're getting closer to 0.6. So we saw three totally different results from making x very large in these three functions. One came out to be a very large number, one came out to be 0, and one came out to be 0.6. Strange and interesting. Now we'll take you through the algebraic techniques that will actually calculate these limits by hand. Just as we worked with algebraic limits at specific x values and certain situations arose, you're going to see certain situations arrive when you take limits at infinity as well. We always start with a plug-in. Now, plugging in infinity is a little bit interesting because infinity is not a number. It's a concept that says x can get as large as I want to make it. So we have to do a little bit of number sense when we do something like plugging in infinity mentally. So what happens in this first function if I plug in infinity? Well, I would get 2 times a very, very large number, as large as I would care to make it, minus 10 divided by 5. And I need to ask myself, what's actually happening here? Well, 2 times a very large number is a very, very large number, and if I subtract 10, it doesn't really do much. It's still a large number. So this is essentially, if I do a little mental math or mental number sense, this is going to be infinity divided by a number. And it should make sense to me that that's still going to be a very, very large number. So this limit comes out to be infinity or does not exist. Okay, that's an easy scenario if it comes up. Scenario number 2, I do a mental plug-in, and I'm going to get 5 divided by infinity plus 3. So essentially, what do I have here? I have a number divided by infinity. Well, when I have a very, very large denominator and a normal numerator that's just a number, the denominator dominates the numerator and brings the value of the fraction down. So this is going to come out to be 0 as a limit. Very, very close to 0. It doesn't actually get there, but that's what the numbers start to approach. Okay, so the first scenario is infinity divided by a number, or negative infinity divided by a number. That's always going to come out to be infinity or does not exist. And the second scenario is a number divided by infinity. That will always be 0 as a limit. Those two scenarios are easy. But the scenario that comes up the most is this one right here. Look what happens. If I do a mental plug-in, I'm going to get 3 times infinity squared minus infinity minus 2 divided by 5 times infinity squared plus 4 times infinity plus 1. A lot going on here, but if you remember some facts from pre-cal, you know that when you square numbers, they dominate any other numbers that pop up in the expression. So an infinity squared is much bigger than a 4 times infinity. So really what you're looking at here is just these first two terms, and those both are very, very large. So this scenario, after you do a mental plug-in, is infinity divided by infinity. Just like 0 over 0, this is an indeterminate form. The limit cannot be determined at this time until we do some more work. And so we need some more techniques that allow us to evaluate these type of limits. And the techniques are a little bit different than they were before. So the first technique you're going to learn here is what's called force factoring. It's called force factoring because you're going to take something that doesn't factor naturally and you're going to force it to factor in a way that helps you evaluate the limit. Here's how it works. You will factor out the largest power of x in the denominator from both the numerator and the denominator. Okay, that's a legal move. It's like dividing the top and the bottom by the same number. So I'm not just doing something to one part of the fraction. Okay, I'm going to abbreviate numerator and denominator here for time's sake. Okay, now let's take a look at what happens when we do that. If I take this example right here, the directions say factor out the largest power of x that occurs in the denominator. So if I look at this example, that is a x squared. And what I need to do is factor out an x squared from the top, the numerator, and the bottom, the denominator. So what happens when I do that? This is why it's called force factoring, because this is not a natural thing to do. All right, the first term is clearly 3. Now, what happens when I factor out x squared from x? Well, I'm left with 1 over x. Factoring is like dividing, so it's like I'm dividing x by x squared. And when I factor out a x squared from 2, I'm left with 2 over x squared. In the denominator, I'm going to be left with 5 plus 4 over x plus 1 over x squared. All right, now what does that accomplish? Well, first thing I'm going to do is I'm going to use one of my limit properties to make this into two limits. We're going to make this the limit as x goes to infinity of x squared over x squared times the limit as x goes to infinity of what's remaining, which is 3 minus 1 over x minus 2 over x squared over 5 plus 4 over x plus 1 over x squared. Now here's what that does for me. First of all, the first limit simplifies to be the limit as x goes to infinity of 1, which is just equal to 1 because the limit of a constant is that constant. So this whole limit ends up being 1. Now I'm in a situation where I'm on scenario 1 or scenario 2 on the previous page. I can do a mental plug-in. 1 divided by infinity basically comes out to be 0. 2 divided by infinity squared basically comes out to be 0. 5 is fine. 4 divided by infinity is basically 0. And 1 over infinity squared is basically 0 as well. So what's left is 3/5. The limit of a constant is that constant. So what I've done when I force factor is I remove the infinity over infinity problem. And we get a nice number 3/5. Now this limit here is a limit at negative infinity. Nothing really changes. I still have a technique called force factoring, but now I have a radical involved. So this is going to involve a little bit of algebra, but my instructions remain the same. I'm going to factor out the biggest power of x in the denominator. In this case, that's x cubed. So the limit as x approaches negative infinity, I'm going to factor out x cubed from the bottom. 1 plus 1 over x cubed Now, let's be a little careful about how we handle the numerator here. Because my variables are inside the radical, I first need to factor out the biggest power of x in the radical, and I need to get it outside the radical correctly. So that's x to the 6th times 9 minus 1 over x to the 5th. I now have the square root of two numbers being multiplied. You'll recall from pre-cal that that's going to be the product of the two square roots. So I can break the square root of x to the 6th times 9 minus 1 over x to the 5th into the square root of x to the 6th times the square root of 9 minus 1 over x to the 5th. The denominator is still x cubed times 1 plus 1 over x cubed. And I'm taking the limit as x goes to negative infinity still. Okay, now we also need to be very careful about how we handle this expression right here. This could be rewritten as the square root of x cubed squared. So in other words, I'm looking at the square root of something being squared, and from pre-cal, one of the awkward truths of pre-cal is that this is not equal to a, it's equal to the absolute value of a. So the square root of x cubed squared is not x cubed, it's the absolute value of x cubed. And the absolute value of x cubed is a piecewise function. It's negative x cubed if x is less than 0, and it's x cubed if x is bigger than or equal to 0. So I need to ask myself, okay, if I'm going to replace the square root of x to the sixth with something, I need to ask myself, where's my x value being evaluated? And since it's being evaluated at negative infinity, that means x is less than 0. So this actually becomes a negative x cubed. Okay, and that's very uncomfortable in the beginning here, but there's some little pre-cal in there that can be reviewed if necessary. And now I'm ready to factor the x cubed away from the rest of the limit and make this into two limits. Once again, we'll make this into two limits. The limit as x goes to negative infinity of x cubed over x cubed times the limit as x goes to negative infinity don't forget the negative sign here, negative square root of 9 minus 1 over x to the fifth over 1 plus 1 over x cubed. Okay, x cubed over x cubed simplifies to be 1 as long as x is not 0, and x is nowhere near 0. X is becoming a very large negative number. So this first limit comes out to be 1, and now we can do some mental plugins. 1 divided by a negative large number to the fifth power is going to be essentially 0, and 1 divided by that same number cubed is going to be basically 0. And so what's left is the negative square root of 9, which is negative 3 over 1. So negative 3 is the answer to this limit. Okay, one more example. This is scenario number 4, which we're going to transform to be scenario number 3. Okay, take a look at this. If you do a mental plug-in, you're going to have the square root of 9 times infinity squared plus infinity minus 3 times infinity. Some number sense says that this number inside the square root is a very large number. The square root of a very large number is still large, so that first part is really infinity, and I'm subtracting 3 times infinity, so this limit is of the form infinity minus infinity. This is also indeterminate. I can't just say it's 0, because it might not be. Not all infinities are created equal, turns out in mathematics. So we need a new technique here. Now, my technique of forced factoring only works if I have a fraction that has a limit of the form infinity over infinity. So I need to make a fraction out of this legally, and the way we do that is by multiplying by something that will create a fraction that creates infinity over infinity. So what comes naturally as an algebra student is to multiply numerator and denominator, and yes, there is a denominator to that expression, it's 1, by the conjugate to the numerator. Okay, in this case, the conjugate to the numerator is 9x squared plus x plus 3x, and needs to multiply numerator and denominator by that conjugate. Okay, the numerator is going to end up being 9x squared plus x minus 9x squared, so just x. And the denominator is going to be the square root of 9x squared plus x plus 3x. Now, at this point, you do a mental plug-in, and you've got the situation infinity over infinity, which means you're now in a position to force factor. And you will do that in a similar manner that you did on the previous example. For the sake of time, I'm not going to go through all the steps to get to the answer because they're very similar to the last example. But I will tell you that the answer comes out to be 1/6, which you can verify by going through the steps to make sure that you've done them correctly. Last thing to talk about here, and you may have already gathered this, but the limits at infinity have a graphical interpretation as well, and here's what it is. The limit, or limits, at infinity and negative infinity of a function, if they exist, are the horizontal asymptotes of the graph of f. So we couldn't tell you the whole story in pre-cal about what a horizontal asymptote really was because it's a limit. Now, if we look at three different graphs here, this first graph, if you head towards positive infinity, starts to level off. It looks like it actually is on top of the x-axis, but it turns out it really is not. It just gets as close as you wish to the x-axis, and our eyes perceive that it actually is on top of the x-axis. So if we had done the calculations on this function, it would have turned out that the limit as x goes to infinity of this function came out to be 0. And what that tells us is y equals 0, that horizontal line, is a horizontal asymptote for f. This function here, we'll call it g, and this is actually the function arctangent x. You may recognize it from last year. It actually has two horizontal asymptotes. Okay, the first one is y equals pi over 2. That's the one that occurs at positive infinity, and the one that occurs at negative infinity is y equals negative pi over 2. Those would be determined by taking limits. Okay, this function right here, let's call it h, has an interesting horizontal asymptote because this function oscillates over and under that horizontal asymptote as many times as you'd like to count as you get farther and farther to the right. So this is a classic example that shows you that a function may cross its horizontal asymptote many times. A lot of students don't think that that's true, but here's a picture that verifies that's the case.